So we come to our second part of chapter 6, that is consolidation theory. So we looked at how we can determine we said after determining the E with respect to the loads which are to the effective stress, which has added after 24, which has been added after 24 hours, or in other special cases after 48 hours. So you come up with a plot of E versus effective stress. I mean, these are effective what? Stresses. Is that okay? So a typical process of void ratio E after consolidation against effective stress for a saturated claim, as we are looking at consolidation, as shown in the figure below. The plot showing an initial compression. This is the initial compression, followed by expansion, then also expanding, also recompression. Okay, so the void ratio log 10 of effective stress relationship for a normally consolidated clay is linear. You can see when it's normally consolidated, it will give you a linear. This will be a linear part. Is that okay? It will be a linear part for normally consolidated soil. If the clay is over consolidated, a soil is over consolidated when the pre-consolidation stress is greater than the overburden stress, the current overburden stress. Okay, you mean that the soil it has ever experienced a loading more than what it is currently experiencing. So when it is experiencing a load which is lower than what it has ever experienced, then we can say it is an over consolidated soil. How does it occur? For instance, if there is a slope cut, or for instance, if they brought the material from a landfill, not from a land, but from a quarry, it may be a maram, a borrow pit. Is that okay? Maybe a borrow pit where they are picking maram. So when they pick maram, the soil which remains will be automatically an over consolidated soil, because it will be experiencing stress, an overburden stress, which is much less than the stress it has ever experienced before. Erosion. When erosion occurs, when there is erosion, soil is taken away. Now for the current state of that soil which remains will be the stress it will be under will be less than what it has ever experienced. That will be an over consolidated soil. Is that okay? Now for the compression curve, ultimately joins the virgin curve, the compression line. So this is the decompression. Is that okay? But still it joins the virgin line here, and then it will still normally go under what? Normal compression. Further compression then occurs along the virgin line. This under using the portion of what? Log the same which is okay here. But this one will be a curve. Is that okay? It will be a curve when it is what? When it's not a log what? Log 10 of effective stress. During compression, changes in soil structures continuously take place, and the clay does not revert to its original length, because the clay is behaved as an elastoplastic what? Material. Okay, it has some plastic strain. It retains its plastic strain. Doesn't go back to its original structure during expansion. So our purpose now to determine what we call the compression index. Okay, the compression is very important. For normal power, it is a slope. It is to be negative, but normally presented positive. It is a slope. Okay, it is a slope of this straight line. Is that okay? The virgin line. The slope, is that okay? So it will be equal to this is the initial E0 or E1 E0. Remember change in Y. Change in Y E0 minus E1. This will be our E1. And divided by, which you come back with this line. The change still will be this side, which will be still a log of rho naught minus log of rho 1. We are going to look at that. So the first parameter, these parameters are needed to predict settlement in the field. Is that okay? So what do we need in the lab able to determine this? What we call the coefficient of volume compressibility is very important. defined as the volume change per unit volume per unit increase in what? Effective stress. So we are saying that MV is equal to change in volume per unit volume again times 1 over per unit change in what? In effective stress. Change in effective stress. So what is change in volume? Change in volume, we said is a change in what? Change in E, which is E naught, which is equal to change in what? Change in E. Change in E. And we said the volume is equal to 1 plus E naught. E naught times the change in what? The change in effective stress, which will be effective stress 1 minus the effective stress naught. Is that okay? Minus effective stress naught. So in this one, that's what it is here. Now for 1 over E, so 1 plus 1 over E is volume. Is that okay? This is change in volume. Change in volume says the same as E naught minus E1. We'll discuss this. E naught minus E1 will be change in volume. The change in volume, E naught minus E1 divided by the change in what? In stress. Now for this, from this, so you can either remember the change in volume. This one also represents H naught. We'll describe that from our expression here. This can be equated to this one. The E naught, where is it? For my expression here, that is H naught, is automatically equal to V. Is equal to, remember this is A. If A disappears, remember this is A times H naught. Now for A is the same, when you cancel out, remember this is V, and our V was equal to 1 plus A naught. Is that okay? So in terms of H to be H naught, remember this one also represents change in what? In volume, which will be H naught minus H1. So it can be done using these two ways, and that is our MV. It's a very important coefficient. Is that okay? As we shall see later. Then compression index CC. Compression index CC is the linear slope of portion of E log plot of E versus logged base 10 of effective stress plot, and its dimension. It has no dimensions. For any 2 points on the linear portion of the plot, E is equal to E naught minus E1 over. So how do we do this? Let's go back to our plot. Let us assume this. We have plots. You have here this point here represents, and it stands for, this is E naught. Okay, represent to log effective stress naught. Then we go to E1, a plot on this one. This is E1, another, and this one stands for log effective stress 1. So how would you get a slope? The slope will be equal to, you can say it is E naught, slope of this line be E naught, value, change in Y, E1, divided by change in X. So the same, this not represent that, which will be log this is not, this is was not original, the initial effective stress minus log log effective stress 1, which will give us CC. But you see that the log of this will be a negative log. Is that okay? So if you plot a negative here, if you plot a negative here, if you pull out a negative here, and you know that if you pull out a negative here, so that you can get, remember I said this is a slope, it's a negative slope. So you pull out a negative here, so this one becomes 1, this becomes not. This is, you interchange these two. Is that okay? So in the end you come up with, because remember, you can, if you get, you interchange it should be E naught E1 as you maintained it up. As you can see, E naught E1, when this is 1, this is not. So if you divide, remember this is less. This is effective stress less than this effective stress. This is after increment of the load. Is that okay? So when you subtract this without interchanging them, without pulling out a negative, to show it is a negative slope, as you see it, not a positive slope. So it is a negative slope here. So it means that this one will be, it will give us a negative value. Is that okay? Now if a negative value, then our CC is not negative, should be positive. Enough. That's why I'm pulling out a negative. So that whatever you get here, it will be positive. So when you interchange this one, now for this one being it, now it changes. That's it has continue. So when you pull out a negative, we shall get E. E naught minus E1, still have a negative outside there, divide by log effective stress fixed stress 1 minus log effective stress, original destination overburden stress, effective stress. So this one, now for if you subtract mine, it is division, logarithm. So you put this under division, and this one, it is a negative slope. So for us, we make it positive. So we shall take it as a positive. Is that okay? Get a positive slope. Now for CC is important. So these parameters, we shall set how we use it. Then the idea is going to show another important paper called the pre-consolidation pressure. We say that if the overburden is less than the pre-consolidation stress, then our material is over-consolidated. Now for the pre-consolidation pressure or stress, the maximum effective vertical stress that has acted on a clay in the past, okay, the effective maximum, okay, the maximum it has in the past. Whenever possible, the pre-consolidation pressure for an over-consolidated clay should not be exceeded in construction. So I said, that's why when you are constructing in wetlands or in swamp areas, we put a surcharge to pre-consolidate this material, so that surcharge should be removed in the construction of the final pavement layers. Why? Because we are saying that we need to pre-consolidate this material. To pre-consolidate this material. So, and whatever we assume that the overburden we have applied will be greater than the load or the stress which we ever use the pavement, so that we don't have a swamp sagging in. Is that okay? We don't have a swamp sagging in. So how do we determine this pre-consolidation? It is very important. How do we determine it? So time is very simple. After plotting, so now after plotting our curve, log E, the first thing we extend this straight path. Okay. After extending, step 1, produce back a straight line BC of a curve. We extend it. Is that okay? So after extending it, then we come and get the maximum point of curvature. Determine point D of maximum curvature of the recompression part. This part, the maximum curvature, the compression part. Then you draw a tangent at that maximum point. Then also draw an horizontal. This horizontal should be parallel to this line. So you take this parallel line using maybe square, whatever, you draw a parallel line to this at this point. Then after that, you bisect the angle between this horizontal line and the tangent. You bisect it. Now for that bisect, where it meets this other line which you extended, you drop that line down, we come out to a pre-consolidation stress. Determine point, draw the tangent to the curve at D and bisect the angle between the tangent and the normal and the horizontal line. Then the vertical through the point of intersection of the bisector and CB or CB or the BC produces, give the approximate value of the pre-consolidation pressure. When you come and draw this line here, I'll give it called the post-consolidation pressure. So you are going to look at in the time path of this example, So in the lab, they did what called the odometer. The compression readings are obtained in the odometer test. Initially, this was the thickness of the specimen, which was put. No, this was the dial gauge. Sorry, this was the dial gauge. Before the application of any stress. Is that okay? So the dial gauge was at 5 millimeters. So but the initial thickness of the specimens was 19. It was put 19 millimeters. So at the end of the test, the water content. At the end of this test, at this point here, the water content, they removed the sample. The time the water content was 19.8%, which has gone the sample. Is that okay? Then plot an E, O cap, and determine the pre-consolidation pressure. Determine and also determine MV for increment between this and this. Is that okay? Determine for determine. We need to determine the MV, and also we need to determine the pre-consolidation pressure. We need to determine also the pre-consolidation pressure. Is that okay? And also need to determine MV, and also need to determine the CC. The pre-consolidation pressure, remember I said it's through plotting. So the first thing is to determine, to plot E, to determine E, remember plot E against log of what? Effective stress, vertical stress. Okay, the effective stress. So the first step is to determine the E naught. So that's one. Now pass through this. The first step to determine E naught. Remember that E naught is equal to E1 plus. Remember this minus this give you change in E for the final. So another thing that we have to determine E1. E1 at the final, with the final void ratio at the final water content. Remember it's going to be saturated. Is that okay? Over SS is equal to 1. Therefore, E is equal to W times GS, which is equal to 0.198 times 2.73, which is equal to 0.54. Is that okay? So the 0. This one is the GS, and this is the water content. At the end, you see it is 19 at the end of the experiment. Determine E1 at the end of the experiment. Is that okay? The E at the end of the experiment. Therefore, E naught is equal to E plus change in E. But if you come back to this equation, that okay? So when we have change in E, we say that change in E over change, which is this expression here. I said, if we go back very fast, for our first expression, this expression here. So we are going to use it. Is that okay? So we have change in E. You know how it comes up about. We have change in H over H original net H naught. Is that okay? So there is the original height has been given us 19 millimeters. Is that okay? So now we need to get the change after at the end of the experiment. The change will be enough. The initial reading was this. So as the input what was reading, now for this was the final reading of the dial gauge. So if you subtract this and this, will give you the change in H at the end of the experiment. Remember, these are cumulative. Our graphs are cumulative. So our change H naught is equal to 5 minus the final reading. Okay, minus the final reading. We again we get this minus this. You get 3.52. The change in naught. Is that okay? So now, what is E? Remember, we said E naught is equal to E1 plus change in E. Let's finish this. Is that okay? So you can substitute in this equation. So when you substitute, we know what E1, we determine this to be 0.15. Know what is 1 is, to give you 1.54, as you can see here. Then we have DE, which we need to find from this expression. We have this and this relationship here. So H naught has been given as 19. The change in H at the end of experiment is also given. So from this expression, be able to determine change in what? Change in E. So if you have change in E from this expression here, with E1, you can determine the initial void ratio before the test. Is that okay? At the beginning of the test. At pressure 0, we can determine the E, which will give us 0. What? 0. Then we come back, we substitute back in this expression. We see that change in E over change this one is equal to this. Now, when you substitute back, when you put this here, you have 1, you have our original height, H, you can come back with this expression. Therefore, I say that our purpose is to determine the change in void ratio, because if you have the change in void ratio at every stage, you can determine E. Is that okay? You can determine E. Why would you determine E? Because E from this expression E is equal to E is equal to E naught minus change in E. Okay. Now for each increment, our purpose to get E is equal to E naught minus change in what? Change in E. Is that clear? Change in E. So our purpose is to determine change in E as you apply the loading. So now let us look at this example here. Let's look at this example now. So at 0, our E naught is E naught. It is this. So after applying 24 kilonewtons square, we get our change in what? Change in H. So the change in H is very simple. It will be this minus this. After will be 5 minus 4.747, which give us 0.523. Is that okay? So now what will be the change? The change in E. If you have the change in H in this expression here, you have the change in H. Using this expression here, you can determine the change in E. So after determining this, after getting therefore the void ratio, at the end of application of the void ratio, at the end of application of this pressure will be the original one minus the E naught minus 0. What? Minus 0. The change 0. We give 0.8. Then we go to the next one. After they increase the loading to 1.075. Now this is the pressure. They have increased the loading. They have increased. Now this is the pressure. This is the pressure. At the end of, they increased the pressure to this. So when they increase the pressure to that, when they increase the pressure to that, what happened? That there was a change in H. It will be just this again minus that. Is that okay? Give the change in H. So after getting the change in H, you can use this expression here, determine the change in E. After determining the change in E, you go to the original one minus 0.5. Is that okay? The original one 0.981. So the 0.0 minus 0.05. To get this value here. Is that okay? Again, do not subtract from here, subtract from this. Remember, it is E naught minus change. Is that okay? It is E naught minus change in E. Is that okay? So you subtract from that, it will be 0.891 minus 0.05, which will give exactly 0.841. So you continue. Is that okay? And you finish all the pressures. Is that okay? Now that you plot, you go to our plot, you get a graph paper. For me, if you have the log graph, you can plot on it. But if you can get a normal graph paper, you get the log of this against that. Now if I put, then you construct. Using the method you have said, you first extend this, you do a tangent here, so you extend this line here, you do a tangent at this point here, do a tangent, then you do an horizontal here, then you bisect, so you do a tangent here, sorry, it's a tangent, then this is a point, a maximum point, you do a maximum curvature, you draw this, you draw this horizontal, you bisect this and this, then you come up with a bisector. Where it meets this line, we give you the pre-consolidation stress. Then on this line you can get any 2 points, determine CC. But they gave you a range between 1,500. Is that okay? You can calculate a CC. Then I think the same thing you do for MVV. You can MVV between that range which has been given and so the any other range. Is that okay? So you determine the MVV. Is that okay? You determine the MVV. By determining the MVV, you come to where the pressure, and I've told you, between, the question was, between 1,100 and 200. Is that okay? So you go to where there's 200 on the graph. Where there's a 200, this is 100, 200 is here. 100 and 200. This point here, you get this reading. Is that okay? Then you come to 200, which is this point here. You get also this other reading. This will be 8.5, which is here. This value here. Then this one is 8.8. When you go to 200, this is 100, 200, which is somewhere, which is about 8.8. Then from use the equations of MV, you determine the MV. Then also do for the next range. Is that okay? Okay, and that's it. Now for these parameters, this parameter is very important in determining consolidation. Let us go now determine consolidation. So you have a layer of soil which is saturated. Is that okay? So let us start with a small layer of soil, of which has a pressure increment. This is a pressure increment. Is that okay? And of thickness change in Z at a distance Z. Is that okay? A distance, the thickness is changing what? Small change in Z. Is that okay? Remember that, as we said, that change in H over H is equal to change in E minus over 1 plus A. This expression here. Therefore, but we need to change the Z. So multiply times change in what? Small change in Z. Now for instance, I just put small change in Z. To get a small, this is a small change up here, which is this